We'd like to tell you how handheld XRF can decrease the time it takes to identify and source physical contaminants found in manufactured foods. This video is part one of a two-part series. Our objectives are to provide you with information to improve quality assurance. We want to teach you how to incorporate physical contaminant identification into your prevention management program. We want to explain how handheld XRF works for contaminant identification, including its benefits, capabilities, and technology, the alloy grade ID method, and the metal contaminant ID procedure. We'd also like to describe other food manufacturing applications for handheld XRF. So, what are some of the physical contaminants found in manufactured food products? The most common ones are slivers of metal, bits of plastic or rubber, small shards of glass, and even chips of stone or ceramic. Typical management procedures to prevent physical contaminants from ending up in finished products incorporate the inspection of food material during production. This is usually achieved with an X-ray or metal detector. When a foreign body is detected, the product containing it is removed. Enhanced prevention procedures include identifying the found contaminant to determine its source. This enables correction of any equipment problems in a more timely manner. Contaminant identification is critical. It enhances QA/QC programs. It helps maintenance monitor production equipment. It helps reduce future delays in production. It helps increase confidence in suppliers. It assists with false claims investigations. And it helps optimize your overall risk management. So how can you determine where these contaminants originate? We'll use the case of metal contaminants to explain. Just a quick look at an illustration of a simple baking production line, from starting material delivery systems to end product packaging, brings to mind the various potential sources of physical metal contaminants found in manufactured foods. Most of the equipment is constantly moving and frequently exposed to high temperatures, humidity, vibration, and the powders, solids, or liquids from the various stages of the food in production. Typical contaminant sources can include augers, conveyors, grinders or cutters, mixers, roller mills, and sorters or packagers. Identifying the source of a contaminant can really enhance your prevention program. Even very small pieces of metal can be identified with handheld XRF analyzers. A found metal object can be identified with XRF by determining its composition, the type of alloy it is, and the alloy grade name. There are 4 simple steps to ID metal contaminants with handheld XRF. First, you prepare the piece of metal in a way that XRF can see it. Then, you select the alloys application on the Ready to Test screen. You position the found object to the XRF's window view, and then you start the test and view the results on the screen. In this case, it's 316 stainless steel. We'd like to tell you more about the benefits of handheld XRF for contaminant identification. It's easy to use, the measurements are non-destructive, you get results immediately. Handheld XRF is portable, which means it can be used on-site or wherever you need to take it, including other sites. It's a cost-effective tool as it is much less expensive than lab XRF systems, and multiple tests can be done on multiple sample types, and it does not require a technician or a scientist to operate. The results are as accurate as lab XRF provides when the sample, prep, and calibration standards used are the same. So what exactly is the XRF measuring to give you results in the form of an alloy ID? Handheld XRFs detect elements as light as magnesium on the periodic table to as heavy as uranium. The most common elements of interest in alloy identification are the light ones as seen in the gold boxes and the medium and heavy elements as seen in the blue boxes. How does the handheld XRF see elements? Well, it has an X-ray tube which irradiates energy to excite elements in the sample. It also has a detector to see which elements were excited and are therefore in the sample. The handheld XRF also has computing capabilities on board, which not only control it, but process the data collected, which then give you answers in the form of an alloy ID. The primary X-ray radiation from the tube excites the element in the alloy sample and are detected by the energies emitted by those elements. Each element, such as chromium, iron, nickel, and molybdenum, has its own signature energy which the detector recognizes. The data processor views the elements in what is called a spectra. If the element is in the sample, the detector sees its energy signature along the x-axis. It can also tell how much of each element is in the sample using the height of its peak along the y-axis. All of this information in a sample is processed and then compared to other alloy compositions stored in the handheld XRF's onboard library. Once all of that information has been processed, the answer appears on the handheld XRF screen. It is given in the form of the identification of the alloy, the list of the elements identified, their concentrations, the minimum and maximum concentration of each element for the identified alloy grade from the library, and the measurement's accuracy. How does the XRF identify a metal contaminant's alloy grade? Alloy grades are defined based on their chemical composition, essentially which elements they contain and at what concentrations. Handheld XRFs can be configured with an alloy calibration, which determines the sample's composition and has libraries with predefined alloy grades, including their minimum and maximum limits. An unknown metal is identified based on comparing its measured composition to those stored in the alloy grade libraries. Here are two examples of how that looks on the XRF screen. One is identified as 304 stainless steel, and the other is identified as 430 or 440 stainless. The grade libraries on board the handheld XRF with the alloy calibration are extensive. There are hundreds of grade definitions which cover multiple international standards. Users can select libraries using UNS, DIN numbers, and other standards. They cover multiple classes of alloys, including those listed. Alloy grade libraries can be edited using PC software, which comes with the handheld. You can also add your own or other alloy definitions. The actual procedure to identify a metal contaminant with handheld XRF is straightforward. You isolate and clean the contaminant. If it's a small one as pictured here, it's recommended to sandwich the sample with thin film and then place it in an XRF sample cup. Using the handheld XRF in a desktop stand, you then place the sample cup on the analyzer window. The integrated camera helps assure your positioning of the sample. The PC software, which comes with the handheld XRF, can be used to control the instrument to perform the test. You simply close the cover and select Start to get your results. Bruker's handheld XRFs, the Titan and Tracer, are ideal for identifying physical contaminants. The optimum one for you depends on what other applications you might want to use the handheld XRF for. To identify physical contaminants, the XRF should have a viewing spot size of 5 or 3 millimeters to accommodate very small samples as well as the larger ones. It should also have the alloy calibration installed on board along with an integrated camera. A desktop stand or the larger benchtop stand with a PC are highly recommended for ease of use when testing very small samples. RTAC's PC software is ideal for more complex contaminant foreign body identification. Sample cups with film are also highly recommended for ease of use when testing very small samples. As mentioned, there are other food safety applications handheld XRFs work well for. You can determine elemental nutrient content in products such as selenium or molybdenum in dietary supplements or iron in animal feed. You can analyze elemental food content for fortificants such as iron and calcium in either liquid or powdered milk, or even iodine in salt. You can screen raw materials and finished products for dangerous elements such as lead, mercury, and arsenic. And you can identify intentional or incidental adulterants, such as lead or chromium in colorants, or arsenic and bromine from pesticides. Threshold concentrations can be programmed into the analyzer to indicate simple pass or fail results on the handheld screen. In addition to the identification of metal contaminants found in food production, the alloy calibration is useful for other applications within the plant. you can screen for hazardous elements in food packaging, such as plastics, polymer films, tin, cans, and cardboard packs. You can confirm metal and alloy grades of incoming and in-service piping, tubing, components, parts, and welds. You can verify that installed process equipment is made of the right material to avoid corrosion and component breakage. You can monitor supplier accountability for quality of purchased components and equipment. You can essentially screen all food contact materials. In summary, contaminant identification for food production is critical. It enhances physical contaminant QA/QC programs. It helps monitor equipment for maintenance. It helps reduce future delays in production. It helps increase confidence in suppliers. It assists with false claim investigations. It helps optimize overall risk management. And handheld XRF is an ideal technology solution for some of food production's challenges. Now we'd like to give you a preview of part 2 of this video series. We will be discussing handheld XRF for the more complex contaminant identification situation, which arises when there are multiple potential sources of the contaminant alloy on the production floor. We'll first review potential sources of physical contaminants. We'll then review the simple alloy grade ID method presented today. We'll introduce the more complex alloy spectral ID method, which is essentially alloy fingerprinting. We will explain best practices in creating a production floor alloy spectral ID library, essentially how to store all the alloy fingerprints. We will also explain best practices in identifying metal contaminants with RTAX PC Software's spectral fingerprint matching program. And we'll demonstrate the spectral ID matching with handheld XRF using RTAX PC software. Thank you for your time and attention. We appreciate your interest in Bruker solutions for food safety and quality. If you would like more information, a budgetary quote, or to set up a demonstration at your facility, please call us at 1-509-736-2999 or email us at sales.hmp@bruker.com. Thank you again.